everybody. Very pleased to see you all. I'm sorry not to be there, but things are like that. But at least I'm able to be here. Yes, we are going to have this session devoted to Work Package 1 and the drug discovery, and in which all 4 ESRs related to this package will present their work. We will begin with the first ESR, Alba Ramos-Llorca. She came from University of Antwerp in Belgium, and her supervisor is Professor Dr. Koen Agustins. She's from Spain. She has a bachelor degree in chemistry and a double master's degree in medicinal chemistry and drug discovery and safety. And she's going to present us her work entitled Activity-Based Proofs Targeting Serine Proteases, a tool for biomarker identification. So Alba, you can start. You remember you have 20 minutes, and then we will ask questions.
Thank you, Amalia. Good morning, everybody. Proteases are abundant on tears, and we know that they maintain ocular surface homeostasis, they activate signaling pathways, and they cleave pro-inflammatory cytokines. But when they are outregulated, they can also disrupt ocular surface integrity, sensitize pain receptors, and induce immune responses. Serine proteases are the most abundant protease family in the human body, and we hypothesize that they play a role in the vicious cycle of dry eye disease. UMC50 is a multi-target serine protease inhibitor that has been previously tested on a tear-deficient dry eye rat model, where the lacrimal gland was removed surgically. UMC50 reduce tissue damage, as here we can see the fluorescent score, and the green line is UMC50 at 5 millimolar concentration, and we can see that it reduces more the tissue damage than the vehicle lines. It also shows to reduce inflammatory cytokines. However, we don't know the mechanism of action of UMC50, and we don't know which serine proteases are upregulated on dry eye disease. We want to use activity-based protein profiling, which is a proteomic tool that uses chemical probes that react covalently with an active form of an enzyme family. If we have a complex proteome, we can use these activity-based probes to label the proteases that are active, and with the right analytical tools, isolate the desired enzymes to identify our target. At our design, we took UMC50 and we modified the terminal pair. We introduced an alkyne to be able to introduce different reporting tags. We designed a library of activity-based probes, and we did 3 different modifications on the molecules. The first one, it's the part that R1 that will go to the specificity pocket. We have basic moieties because we are targeting trypsin-like serine proteases, which they can interact with an aspartate on the active site. We also included lysine and arginine analogs that are the natural substrates of trypsin-like serine proteases. We also modified the phosphonate, the substituents on the phosphonate aryl, that it's the part that reacts covalently with the serine on the active site, and it will change the reactivity and therefore make our compounds more potent. And the last part, R3, that is the reporter tag. We have the alkynes on the activity-based probes precursors, and then we use biotin and the biotin. However, we could also introduce other reporter tags as fluorescent moieties. I will explain a bit the synthetic pathway towards our molecules. We start with an aldehyde, an alkyl carbamate, and the triphenylphosphate, and Lewis acid as a catalyzer to form the phosphonate bond. We deprotect on the next step to later introduce the guanidine, and the last step will be to deprotect these two Bog moieties also with TFA. Once we have the ABP precursor, we, by click chemistry and the azide of the reporter tag, we can finally synthesize our activity-based probes. We tested all our compounds in a panel of 7 serine proteases, 2 non-trypsin-like serine proteases, neutrophil elastase, and chymotrypsin, where we can see that our compounds, as we suppose, they are inactive on those proteases. And then we have 5 trypsin-like serine proteases, and also catepsin G, which also has chymotrypsin properties. I will focus on those that are more potent and more interesting, which are arginine, that is a natural substrate of these trypsin-like serine proteases, proline lysine, that is an activity-based probe that has been previously described in literature as a promising tool, and our probes, the benzyl guanidine, the phenyl guanidine, which they only differ in this carbon here, and the piperine guanidine. As we can see, for arginine, this compound, I will focus on the R1, on the 3 different modifications, starting from the R1 substituents, that is the part that was going to the specificity pocket. Arginine is a compound that is active on all the trypsin-like serine proteases, as it's the natural substrate. The proline lysine has similar activity as the arginine probe, and we can see that the benzyl guanidine compound is more active in most of them, but a bit less active on thrombin. Phenyl guanidine has similar activities as the arginine compound, but it's inactive in thrombin. However, thrombin is a coagulator factor, so it might be interesting that we are not inhibiting this enzyme. And finally, piperidine guanidine, that is active on trypsin and thrombin. And for now, we will discard this compound because our goal is to identify which serine proteases are active and not only target 2 of them. So for now on, I will just focus on arginine, the benzyl guanidine, and the phenyl guanidine compounds. The second substituent that we change is the substituents on the phosphonate. As we introduce different moieties, electron withdrawing substituents, we make these phosphorus more reactive and therefore more potent compounds. And this happens when we introduce the acetamide or the chlorine. In general, we see a tendency of increasing activity when we move towards the chlorine in all the series. And therefore, we chose the chlorine as the best substitution. And finally, we move towards the activity-based probes, the reporter tag. These graphs only show that when we move from the precursor to the activity-based probe and we introduce the reporter tag, we don't see a decrease on the significantly decrease on the activity, and therefore we can see that introducing the reporter tag doesn't have an effect on the serine protease. So here a summary of our first selection. It would be on the specificity pocket, depending on the protease that we want to target. It would be arginine, the benzyl, or the phenyl guanidine. For the phosphonate aryl, we would choose chlorine because the compounds tend to be more potent with the chlorine. And as reporter tag, just for the ease of working with it, we chose des-thiobiotin over biotin. Activity-based probes are irreversible on the definition because they react covalently with the active form of the enzyme. However, we do not always observe this behavior. With arginine, and this happens with the benzyl-guanidine compounds, that surprisingly they are the most potent in most of the proteases, but they show a reversible mechanism of inhibition. Only in the panel that we've used, only they are irreversible in UPA. Arginine, it's irreversible in all the proteases that we chose. However, it's not active on cathepsin G. And the phenylguanidine, it's irreversible also in all the panel that we've tested, but inactive on thrombin. Therefore, depending on the purpose of the use of these proteases, we would have to use one or the other. And what can we do with these activity-based probes? This is some preliminary results on another project that we are working on irritable bowel syndrome. First, in the first square, we used the chlorine and benzyl-guanidine probe to see if we could visualize the proteases on gels. And as you can see, for some, it's more visible than others. So with the one that we are having more troubles is with thrombin, but again, it's a coagulator factor, so it might not be that interesting. And on the other square here, we checked the inhibitory activity on rectal biopsy supernatants. So in the white ones, we have the healthy volunteers. In the low gray, low gray, we have IBS low patients, and on the dark gray, we have IBS high patients. We can see that when we treat when we test the trypsin-like activity on these samples, with the vehicle, we have high trypsin-like activity. However, if we inhibit these samples with our compounds, either A, benzyl-guanidine, B, the phenylguanidine, or C, arginine, we can lower the trypsin-like activity. So this is a proof of concept that these activity-based probes, we can use them to visualize trypsin-like activity on biological samples. So in summary, we design and synthesize activity-based probes based on a serine protease inhibitor that that we have proof of concept that it can reduce inflammation on a dry eye model. We determine the IC50s of all the compounds that we have, and also the kinetic evaluation, proving if they are reversible or irreversible inhibitors. And the next step would be to try to see, to label proteases on dry eye samples to prove, to use them as biomarkers. And here, a reminder of the 3 more promising probes that we have in hand. I would like to thank everybody that was involved in this project at the University of Antwerp, in our group in medicinal chemistry, and also in the group of medical biochemistry, and also our collaborators in KU Leuven for the project of IBS, and all of you for your attention. And if you have any questions. Hi, Mike.
Thank you. And I think now the advisory board is going to ask some questions.
Yeah, Mike. Thank you.
And what I was waiting to hear was effects on the tissue, number one. And so the irritable bowel stuff is actually quite important. but you don't really know what these biomarkers are actually doing to the epithelium of the
No,
of the gut.
we would like to try to use these activity-based probes on dry eye tissue, on the eye tissue, to see if we could.
And one other thing that I think is interesting and of concern to this consortium, we were very concerned when we were developing cyclosporin, because that's a protein. We were very concerned as to what the proteases on the eye were going to do to that drug. You know, in fact, we thought it may just eliminate the drug and there would be no effect. So, you know, your work might indicate that there would be a test run on any protein-based drug to put on the eye just to see whether or not it could stay intact enough to be effective. Yeah. Very good job.
Thank you.
So Alba, thank you. That was a lovely talk.
Thank you.
You mentioned at the beginning a rat dry eye model. Is that work that you plan to do?
No, this is work that was done previously before I started my PhD.
Aha.
Yeah.
Okay. And which of the serine proteases were the predominant ones in that model? Can you?
I think on that paper they only tried tryptase, if I recall correctly.
Okay. Thank you very much.
No problem.
Thank you. Just a quick question. Thank you. Nice talk.
Thanks.
How do you explain the difference of kinetic behavior of your different probes?
Yeah, that's something. It was really surprising when we saw, that in the first ones I did, it was UPA, where first I only had the benzyl guanidine compounds, and I tried with UPA, where they show the irreversibility that we were hoping, because the phosphonate should react covalently with the serine. And then I tried it on tryptase, and on tryptase it was reversible. And we still, up to now, we don't know why this happens. I also did jam dilution assays to see, to corroborate what I saw on the kinetic curves. And indeed, it's reversible in most of the proteases, but irreversible on UPA. Of course, we could also amplify this panel, and it might be reversible also in other proteases, but on the panel that we have, it's only irreversible on UPA. And I don't know, it's possibly, how the conformation on how it arrives to the active site, or, I don't know.
Idea about the quantity of proteases in different ocular surface samples? I guess that you plan to use, I don't know, tears, cells?
Unfortunately, we don't have the available eye samples that we need. We are looking for collaboration with somebody to be able to test these activity-based probes on dry eye samples. So we didn't have the opportunity to have dry eye samples to see the proteolytic activity on them.
And for you think that it's better to start with the mice model or directly on humans samples? Of course.
If it's on samples, I think it's better just to start with humans. So we have more relevant information that if we start with mice and then we switch to humans, and it might be different. So if you have to put the compound on somebody, then it's better to start with mice. But if it's with just samples of tissue or tears, then I would say it's better with humans.
Okay, thank you.
Okay, so there are any other questions?